So simplifying factorials, questions that I just want to make sure you guys are following, because we often have to do these ratio tests. Comes up everywhere with these Taylor series because we want to find the interval of convergence. And if these factorials come up, we are often simplifying something like, let's write it as like 3n quantity factorial over, if I plug in an n plus 1 for that n, it'll be 3 times the quantity n plus 1, and then those two together, factorial. And so our goal is to just simplify this. So always be mindful of these parentheses, especially the common mistakes that I see when you're doing these ratio tests and interval of convergence, it's forgetting this parentheses. So you will just have 3n plus 1 is what a lot of people end up having. If you keep the parentheses there, we'll end up having a 3n plus 3. So our same order of operations that we've always had apply, right? We got to work from the inside parentheses out, and that's where we get that 3n plus 3 first. So no factorials needed, just kind of a common pre-calc skill that can get a little weak after a few years, not practicing it too much, making these n plus 1 substitutions. And now we've just got factorials, essentially, to work with. And our goal with factorials is, remember, always start with the biggest one. So 3n plus 3. If this were a 3n minus 3, that's smaller. So we would start with the top and then work down. And remember that our 3n factorial since the 3n is inside the parentheses, it's part of the factorial. So it's going to be 3n times 3n minus 1 times 3n minus 2. And it's going to keep going all the way down until it gets to 1. And likewise, 3n plus 3 factorial. Same thing, except now I'm starting with this 3n plus 3. So we can keep writing out our terms, and eventually you realize after I get 3n plus 3, 2, 1, the next term essentially kind of brings us back to the previous one, to the smaller factorial. And it will keep going, 3n minus 1, 3n minus 2. And it keeps going all the way down to all the other terms. And so what you want to do is to simplify factorials, we are factoring factorials. It's kind of the reason for the name, is that it's just an infinite product. Since I'm multiplying all these terms together, we can factor out as many of the terms as we want. And then what are we left with? The smaller factorial. Right? The product of all of these guys is just those guys up there. So if we kind of continue from here, the way we write that, we keep the 3n quantity factorial as it is. And then this one in the denominator, I'm factoring out those 3 terms. So I'm just going to write them individually. A little bit of a pain with 3 of them. Write them all out. And then what's left, this guy, I'm still multiplying by the rest of those guys. And we could, if you wanted, you could write all of this out on the top. You could write all of this out on the denominator and then cancel them all out. Or to use shorthand, well, this 3n times 3n minus 1 times 3n minus 2 is just now 3n factorial. So from this bottom factorial, we factored out those 3 terms. And what is left, still a factorial. indexed from wherever we stopped at. So we kind of stopped at 3n, and we know we still have all of those terms, so those are included by this notation of the factorial. And since these guys are now the same, they divide. So it's just 1 over 1, or yeah, something over itself is just 1. And so our simplification is just going to be 1 over 3n plus 3, 3n plus 2, times 3n plus 1. Anyone still writing or any questions on that? Okay, so re-indexing Taylor series, we've talked a little bit about. Let's go over it again and see where it comes up. I think I mentioned it last week, but it's been a little while since we've seen it. And now that we're going to be doing more of these Taylor series, especially derivatives and integrals, we're going to have to do it quite a bit. So the idea is this, is if I have some function that's given by a Taylor series or power series, then if I compute a derivative, well, by our rule, we've got this. But where should n start here? So if you write that out, remember, it's just c0 plus c1x plus c2 x squared plus, and it goes all the way up. And so when I take my derivative, this 0th term goes away. And what are we left with when we start? We're just left with c1. So c1 is our starting value. And you should also kind of recognize, like, it wouldn't make sense to start at n equals 0 because, you know, that n equals 0 essentially kills that term, which is the equivalent of this term dropping out when we take a derivative. So when we take derivatives, it sort of changes the starting point for our series to n equals 1. Which is a little weird because we're starting at 1, but what is the first power of x? When I plug in that 1 here, we get a 0th power. We get our constant term. And it's something we don't quite like. We kind of want the constant term to correspond to x to the 0. Does that make sense? It's kind of just our standard practice, at least. I mean, on tests and quizzes, if it were handwritten, right, this for me, you know, you take a derivative and you have a correct Taylor series, that's good. But the problem is, well, we've got these multiple choice questions on WebAssign, on the quizzes, on exams. And so if you come up with a correct Taylor series, but your index is starting a little bit different, you can have the correct Taylor series, but not have it in the correct form. You're not recognizing the forms they have. So you want to get a little bit of a practice of kind of understanding and being able to think ahead and notice that, well, if I re-index this, what's going to happen? So let's go through that just for this first derivative. This is a generic example. We'll keep our constants as Cn, and then we can do a concrete example if we want. Okay. Well, so what do we want? We essentially just, it's like doing a U-sub with just a linear shift. So, well, right now our counts go like this. We start at n equals 1, then we go to n equals 2, then we go to n equals 3. And of course, what do we want? We want to start with some number. Let's call it k. Pick what your favorite indexing variable. And I want those to match up, but just starting at 0. So when n equals 1, I want k equals 0. N equals 2, k equals 1. N equals 3, k equals 2. And so what does that mean? How are we going to shift these? Well, it just means that k is 1 less than n. So k is 1 less than n. In other words, we can also solve that for n. So n is 1 more than k. And all you have to do is then essentially use this substitution. Substitute all of your n's for k plus 1. So it's going to look like this. F prime of x is equal to the sum. Oops, didn't mind to write that in. Let's rewrite it. Prime of x is equal to a sum. My cn's, well, what is n? It's just going to be c sub k plus 1 there. That n now becomes a k plus 1, and then that n becomes a k plus 1. So we will have k plus 1 minus 1, and we will just get k there. And we forced it to start at 0. And the nice thing, of course, infinity, when k is infinity, n is also infinity. So infinity is always at the top. And so that's all it is. You know, just a basic, it's like doing a u sub. We're just changing the variable and shifting things around a little bit. This bottom one, you can also kind of see if our n, if we wanted to do an extra step with that bottom indexing, well, our n was k plus 1. So if we kind of just worked with that equation on the bottom that it's written, of course, we get our k equals 0 is the equivalent statement of that, which is how I got it. So for example, if we do something like f of x is, let's see, let's start at 0, infinity, and let's pick some indices. Let's do something like minus 1 to the n. Let's do 3 to the n plus 1 next to the n over n factorial or something like that. And for practice, let's say we want to find f double prime of x. So let's actually take 2 derivatives. So our indexing is going to be a little bit different in the previous example just because we only took 1 derivative. So if we take 2 derivatives, even if you kind of naively keep n equals 0 there, let's see what happens. All of these terms with n's in them are just constants. Then we will have times an n next to the n minus 1. This one you do want to be a little careful about, at least with the index starting at 0. We want to simplify. You can simplify this n and n factorial. You just have to be careful about the 0th term, because what is 0 factorial? It's 1. So even if I started at 0, that n equals 0 will kill everything, and it'll just be 0. So it's not needed. So we commonly write the power series starting at n equals 1. And what we're going to do, what I'm going to do now, is write it like this. So what did I do there with the simplification? This is just, again, our factorial simplification. I'm doing it in a different color here, because we have this n over n factorial, which we can write as n over n times n minus 1 factorial. So I factored out that n from the factorial, and then the rest is n minus 1 factorial, and those two guys will divide. And so we're left with our n factorial on the bottom. And now it makes sense. When n equals 1, it'll be my x to the 0, so our constant term. And again, remember, 0 factorial is just 1, so this makes sense in the denominator. We're not dividing by 0 or anything there. And if we compute another derivative now, constants all remain. And we're just doing our power rule. I'm kind of keeping these constant terms off to the left and then giving myself space to just take that derivative and get that extra factor of n minus 1. And again, if you continue the series and you think, well, let's just keep n equals 1, and you check yourself, well, what happens when n equals 1? This term will be 0, and this will be 1, so that 0 will kill everything. And so it doesn't matter, and we can actually rewrite the series. Minus 1 to the n, 3n plus 1. And again, these factorials, if I'm starting at 2 now, then I can divide my n minus 1. I can factor that out again, and we'll just get an n minus 2 factorial. Anyone still writing? Okay, so let's write that on the top. Oh, sorry.
All clear.
Cool. So let's write that at our top. We're starting with this guy. Minus 1 to the n, 3 to the n plus 1 over n minus 2 factorial. X to the n minus 2. And our n is starting at 2. We don't quite like that. Or at least we've come this far in the problem. We're trying to find a Taylor series for the second derivative of this. And this doesn't look like any of the answers in the multiple choice. So what do we do? What do we want to look for? I would say always match, look for this starting value. There might be answers in the multiple choice that start with an n equals 2. But if these don't match up, right, you may find that, okay, this answer starts with an n equals 2, but then you compare what's actually written and they're different. So could be an indication. Check your work. If you trust your work and you're pretty sure you've done everything right, then that might be just a distractor trying to trick you. And then you might look and see, well, none of these other answers start at n equals 2, and none of these other answers look like what I have written. So what do you have to do? Re-index. That's kind of the dead giveaway. I've seen a lot of these multiple choice where maybe there's like one answer with n equals 2, starting at n equals 2, and then like 4 answers start at n equals 0. So it's kind of another, not definite, but the probability of what the correct answer is means you should probably re-index your solution to see what happens, what it looks like starting at 0. So again, you can write out some of this if you want. N equals 2, n equals 3. It's going to go up. And what do we want? We want k to start at 0 and then go up to 1. And also, if it helps, write out some of the terms. When I start n equals 2, that's going to be minus 1 squared, positive. We will have 3 cubed over 0 factorial is just 1, and then x to the 0 is our constant. N equals 3 when I plug it in will give me a negative 1. 3 to the 4th over 1 factorial is still 1. And then I'll have x to the 1. Likewise, n equals 4. 3 to the 5th, positive from that negative 1. And then we will have a 2 factorial in the denominator. So you can always write out a few terms if you want. This is another way people do it, is you can literally just write out the series you want and then just come up with a new way of writing the power series. If you're comfortable doing that and you think that's quicker for you, just going from an expanded form of a power series and then writing a sort of closed form sigma notation of it. For me, I think it's a little quicker to do just re-indexing, because we want this term to be n equals 0 or k equals 0 to correspond to our 0th degree of x, instead of having that be our second value of our index. So from this, k is just 2 less than n. If n starts at 2, I want to subtract 2 from n. And likewise, n is k plus 2. And all you got to do is substitute for all of your n's in this expression, k plus 2. And of course, k plus 2, when I subtract that 2, k will start at 0. We'll have minus 1 to the k plus 2, 3 to the k plus 2 plus 1, give me k plus 3. And then here I'll have n minus 2 is k, or of course, k plus 2 minus 2. Gives me that k factorial. And then I will have x to the k. A big thing to kind of look for with these, it is often the case where we want both the index to start at 0, and then you notice that the powers match up with that. It's always x to the k. So that way, k equals 0 is our constant term, k equals 1 is our linear term, k equals 2. We like it when that is just a k, so it'll match up with the indexes. The last thing that you will see is messing with these minus 1s. So this may not be an answer listed. It's correct, but again, it may not appear there. The only difference you might see is simply taking this minus 1 to the k plus 2 and factoring out 2 powers of minus 1. Right? This is just basic factoring of exponents. And of course, minus 1 squared is positive 1. So it's still just minus 1 to the k. So that plus 2 actually isn't even needed on this guy. So it'll probably be written like this. Anyone still writing? Or any questions on that? Okay. Let's do one with an integral. And I want to complete our table. So there's essentially just 2 questions, or 2 classes of functions that we want to put on the table. I think one of them we've encountered a couple of times, and we've worked with a couple of times, but I don't think we've completely come up with the power series for it. And that's natural log of 1 plus x. Sort of the last big class of functions that we don't have a Taylor series for. We've got our trig functions, our sine and cosine. I think we even started to do tangent. Tangent's not one you have to worry about too much, because to do it properly, you really want to divide sine and cosine. And dividing power series, I'm not sure if we'll get to. We do want to get to adding power series. That's another skill we'll see. But we've got our trigs, we've got our exponentials, e to the x power series, and then sort of the natural log. We want some sort of power series for natural logs and see how they look. And it's easiest to start with shifting your natural log, just so that here, natural log when x is 0, we'll get natural log of 1, which is 0. So it passes through the origin. And so we can nicely enough take this as our a value. Since this is a nice, easily computable value, I can center this series at 0 and come up with a Maclaurin series for it. So the hard way would be to take derivatives and to keep doing successive derivatives, evaluating it at a equals 0. We saw this in the past and did like a degree 3 polynomial for this. One of the tricks with this is to recognize that if I take a derivative, what do we get? Just 1 over 1 plus x. And this is a known power series. So let me find my sheet here. Yeah. So this is our known Taylor series power series representations. And again, feel free to add more of these to your own list if you want, that you do on your own or you do in your work, that you think, was important to remember, or important skills you kind of developed in terms of figuring that out. And, write those notes to yourself of how you figured it out. So we figured out that, well, this 1 over 1 minus x was our nice geometric series. And if I just replace that minus with a plus, by some algebra, it'll just give us an alternating geometric series. So since we have a power series for this 1 over 1 plus x, all we have to do is integrate it to find natural log of 1 plus x. So if 1 over 1 plus x is equal to the sum of minus 1 to the n, x to the n, and now starting at 0 to infinity, when we integrate both sides, we should get natural log of 1 plus x is going to be the integral of this series. And I can move the integral inside. We integrate term by term. And what do we get? We should get x to the n plus 1 over n plus 1. And we're missing one thing. So we missed this when we did sine as well, since we got sine from cosine by integrating. Whenever you integrate, you have to remember a plus a constant. And this constant is outside the series, so it's not like being perpetually added. Because what's happening now with our indices? Converse to the derivatives, we're actually gaining more terms, potentially gaining a constant term. And here, when n equals 0, what's my first term? X equals 1, right? My n equals 0 now corresponds to a degree 1 term, so there could be some degree 0 term lurking. And how do we find C? We usually find C by checking known values. I don't think I have space for it. Let's just use a new sheet. So we've got natural log of 1 plus x. I'm going to put the c on the outside on the left here is equal to a constant plus our series. And if you want, you can write that out. So what's this going to look like? It's going to be c plus, when x equals 0, I'll have x to the 1 over 1 When n equals 1, we'll have a negative x squared over 2. Next term, n equals 2, will give me x3 over 3. And it'll keep alternating. And what is our known value? Well, I know that at our point that we chose, at x equals 0, we just get a y value of 0, which means if I evaluate my Taylor series at 0, I guess you could put some of those as negatives. What do we find? We find our constant is just 0 as well. So sometimes that constant is a number, and in certain situations you have to, sometimes the number or the constant doesn't fit in well with the pattern of the indices and the coefficients based off of that. So sometimes the constant is just left outside. Sometimes you can kind of work it in as the full power series and then work it in with all of those. In this case, it naturally works in because it's just 0. So that is our series. We can add that to the list. Let's not add it yet because let's make sure our index and our powers of x match. Let's just try to get in practice of writing these power series so that it's x to the n, x to the k, so that the starting power of our index matches the starting power of x. Is a kind of a standard form to write these in, as we saw with our derivatives. And now we just have an integral. So we've got another reindexing thing, but it's just going to be in the opposite order. We're starting at 0 and then going up to 1, 2, and what do I want to start at? In this case, we actually want to start at 1 because this term was 0. Since I didn't have any x to the 0 term, we start at x to the 1, x to the 2, x to the 3. So now our k is going to be 1 more than that. And so what is our sub? K is just n plus 1, and is k minus 1. So our natural log of 1 plus x. If I plug in k minus 1 here, I would add that 1 over. So our k's start at 1. We'll have minus 1 to the k minus 1. And then we would have x, k minus 1 plus 1, which is x to the k. And then k minus 1 plus 1 on the bottom gives me a k in that denominator. So both of these forms, again, both are correct. I think this one's a little more common, just because we like our powers of x to match up with the index. In this case, it is just natural to start at k equals 1 because our constant term was just 0. Let's go ahead and add that to our sheet. So we've got natural log 1 plus x, and that is equal to minus 1. I'm just going to change the k's to n's now. There we go. What's our radius of convergence for that? So remember where we got it from. Since we got it from this guy, radius of convergence is going to be minus 1 to 1. And you can type or write integrate 1 over 1 plus x is how we found it. Any questions? Or anyone still writing? Okay. How are you guys feeling about coming up with these power series? So let's see, where's my sheet of list of problems and topics I wanted to go over? There's a couple about evaluating. There's a couple on adding power series, which can get a little tricky. The remainder theorem we can get to at the very end if we have any time. And let's see, so on the quiz tomorrow, it'll be something like finding power series. How comfortable are you guys doing that? Like using our known sheet. I think you guys are practicing this on WebAssign a little bit, where you had, you know, things that looked like this, where it was like something like 1 over like 9 plus x squared or something like that. And then you had to maybe start with some of these series and modify it to come up. You guys feeling comfortable with that? You guys want to see any examples?
If you could do another example, that'd be great.
Sure. Do you want one that looks like these rational functions? Something that looks like, there's always things like x squared e to the x, cosine of x. Maybe we could do a couple. Let's do one with one of these guys. So let's see, find the power series. For, let's do something like f of x is equal to, say, x squared over, let's say 16 minus x to the 4th. So usually when you see the function, you kind of want to match it. Like, what does it look closely like? There's no exponentials, there's no sines or cosines or natural logs, so all of these we don't need. You want to be thinking I should be able to modify it to make it look like a geometric series. So we've got this x squared in the top, which is a little weird. The numerators are kind of nice though. As long as there is just a power of x, if we're not adding or subtracting, you can always consider just factoring out that numerator. Into something like that. And that gets us a little bit closer, right? Now I have a 1 in the numerator, and it's a constant minus something like x to the 4th. And well, this constant we want to be 1. So what we have to do is factor out this constant. And remember, so I'm factoring out purely from the denominator. And so within the denominator, you're kind of forcing another fraction here with this x to the 4th term, since this 16 would distribute. And that's about all there is to it. We could essentially pull out the power series now. One other thing we might want to try is to just write this as x over 2. So 16 is 2 to the 4th. Quantity to the 4th. I don't know if it'll actually help us. Might not. Let's keep it though. So we've got done our algebra, purely algebraic tricks for this guy. And we've got it 1 over 1 minus something. And that's essentially what this power series is. 1 over 1 minus something. The something here is just x. Gives us our geometric series. So of course you want to reference that. And so modifying this, we should have that f of x should be, our x squared minus 16 is going to stay outside for the moment. And we're replacing this guy with a power series. So we've got a sum n equals 0 to infinity. And our something isn't just x, it's x over 2 to the 4th. So we should have x over 2 to the 4th, and then all of that to the n. And I'm just overusing my parentheses there for the moment, just to keep the algebra organized. So this was my something, right? My x over 2 to the 4th is replacing my x's raised to the nth power. And then when we simplify, we will get x over 2 to the 4n. So this is a good power series. Well, I guess there's this x squared over 16, which we would like to integrate inside. Again, I've seen some of the answers on WebAssign where sometimes they leave the constant out front. We do usually try to pull in the powers of x. So I'm actually going to rewrite this. It looks like the x over 2 isn't helping us, at least in terms of rewriting it. It's a good answer, but I don't think it's a common answer that might be seen on the WebAssign. So I think they usually write it as, this will just be x to the 4n divided by 2 to the 4n, which is 2 to the 4 to the n, or 16 to the n there. Everyone comfortable with how I got that? Of course, the alternative would just be to take this term here and replace that. So it should be, the sum of this guy to the n, which is essentially what we did here. So same thing still, just different algebraic notations there. The reason for that being nice is that now I can kind of integrate these two terms. So if I multiply these terms inward inside the sum, we will have x to the 4n plus 2 over 16 to the n plus 1. And this is a good answer. Again, up to re-indexing. It's kind of hard to re-index this now because there's an x to the 4n, right? My x to the 0 starts at x squared. But when x equals 1, we will have x to the 6th. So because the powers of x aren't increasing at the same rate as these guys, they're increasing every 4. I don't think a re-indexing for this is necessary. It wouldn't really help us, even if we had starting at n equals 2, and this one gave me a degree 2. As soon as I increase this increment once, the power of x is going to increment by 4. So the powers of x are never going to match up perfectly with that index. So it's best to just leave it like that. Okay, so let's try one. Let's do 2 more. I don't know how long that'll take us, and then maybe we'll get started on the remainder. Let's do one, just talk about polynomials real quick and the binomial theorem. I don't know how much we're going to test you guys on the binomial theorem, especially because some of the problems in the book that I've seen are using the binomial theorem with like fractional values, which gets a little weird because we don't know what fractional factorials are, so we kind of have to get around the notation for it. Suppose I have a polynomial. Let's do this a little quickly. Let's say I've got, let's make one up, 7 plus 3x minus 10 x squared plus, let's say 2x cubed. Here's a question. What is the Taylor polynomial or Taylor series? For this function? And let's say specifically at x equals 0. The answer is the same function. Why? Well, right, remember, what are we trying to do with these Taylor series and Taylor polynomials? We're trying to use polynomials to approximate a function. So if my function is a polynomial, the best polynomial to approximate it is the exact same polynomial. The only thing you have to change is if, for whatever reason, we were trying to change the degree, which would never happen. Almost never, right? We're never going to use a degree 2 polynomial to approximate a degree 3 polynomial. Usually not going to happen because calculation based, we like our polynomials. The whole purpose of doing all this is that I can compute, reasonable powers of x to a certain degree and approximate. So we really only need to change when we change the base point. Let's go through this first part and justify it first, though. Right, what's going to happen if I compute f of 0? I have zeros in for x, and I get my constant term. And when I take my derivative, sorry, that should have just been a 3. And of course, when I evaluate it at 0, we just get our first term, and then our second derivative is going to be minus 2 times 10 minus 3 times 2 times 2 times x. And of course, evaluating, we will just get our minus 2 times 10. And I guess there's only one more. Let's go ahead and do it. F triple prime is going to be minus 3 times 2 times 2. And then so F triple prime at 0 is just that. And by our formula, so this term's our C0. This term is our C1. Our C2 is the second derivative divided by 2 factorial, or just 2. So that term's going to go away. So our C2 is negative 10. And likewise, our C3 is F triple prime divided by this 3 factorial. So we're going to divide out by the 3 and 2. Why do we have a negative here? Should that one be negative? I think I missed that. That should all be positive, right? From that positive. And what are we going to get? the 3 and 2 will cancel. And so we just get a 2. So you can see that, right? These are designed specifically because we want the coefficients, oops, to match up with those values. We've got our 7, our 3, our -10, and our 2. All matching up exactly for that polynomial. The only difference is now, so what happens is what happens if I want to change the base point? Sometimes the algebra can get a little hairy. So let me see, I pulled up one. This is something you'll have to do on the website. And I give it a degree 4. So your guys' numbers might be a little different. This is WebAssign 8.7 part 2. I think this one's due tomorrow. And I think it's number 2. It says f of x gives us a polynomial at a equals 1. So really what we want to do is, the idea is I can write f of x as some constant, some constant plus our degree 1 constant, x minus 1, plus a degree 2 constant, x minus 2, x minus 1 squared, excuse me, plus degree 3 constant, x minus 1 cubed, plus our degree 4 constant. We could do this entirely without any calculus. What would we have to do? You could expand each of these guys out, collect all your like terms, collect all your constants, and rewrite it in this form. And then come up with a bunch of systems of linear equations or systems of equations for your constants and solve that. Very similar to what we did with partial fractions, where you're collecting, the linear powers of x. Because when I square this guy out, I'll have x squared minus 2x plus 1. So that minus 2x will give me a linear power of x. And so we'll come up with all these relationships for the constants. We don't want to do that, though. Why not? It's a horrible pain. Algebraic mess, right? We don't want to square that out, let alone cube that guy out and do a degree 4 expansion. So we can just go through the process of this guy and go through the process of finding our Taylor series by evaluating our derivatives at a equals 1. So our f of 1 is, the nice thing at least about evaluating at 1 is it's not going to be, not hard computationally, right? It's going to be 1 minus 4 plus 4. Essentially, when you evaluate at 1, it's going to be the sum of whatever constants are there, just because x to 1 to any power is going to be 1. So we get 1. We compute our second derivative, or excuse me, our first derivative. Four x cubed minus 8x, 4 goes away, and then we evaluate at 1. So we'll get 4 minus 8, -4. We compute our second derivative. It's going to be 12 x squared minus 8. Evaluate. And we get 4 again. And then we've got our third and fourth derivative. So one thing to note is that whatever the degree of the polynomial is the highest degree you'll have to go to. So I didn't write a plus C5 because we won't need any degree 5 polynomials no matter how we shift it. A degree 4 polynomial will always be a degree 4 polynomial, which means we only need at most 4 derivatives. So a little bit of work. Let's see, so our third derivative is going to be 24x. And so f triple prime of 1 is 24. And then our fourth derivative is just going to give us that constant of 24. So if it helps, box out your evaluations. I guess so far we've usually been doing this in a table where I've had the f prime of x on one side and then evaluated on the other side. That might have been a better way to kind of organize it so we can kind of keep track line by line of where we're at. I just went ahead and evaluated after I took the derivatives. So I'm going to box those out just so I'm aware of where they are, and then come up with the corresponding constants from our formula. And of course, since that one's constant, it's the same as evaluating at 1. And so our C0, I didn't box yet, it's going to be that guy. Our C1, again, is going to be f prime of 1 divided by 1 factorial. So the first two are always easy. The first two constants always match up with whatever the value of the function is at that point for our 0th order, and the value of the derivative at our specified point for the first order. It's only C2 and beyond where we got to remember to divide this. So we take 4 f double prime of 1 and divide by 2 factorial. Likewise, C3, we're going to take 24 and divide by 3 factorial. So 3 factorial, 3 times 2, which is 6, gives me a 4. And then C4 will give me 24 over 4 factorial. 4 factorial, so 3 times 2 was 6, times 4 is 24, so that C4 is just 1. A little bit of work to do for this guy, but then all we got to do is write it out. So our f of x is going to be 1 minus 4, x minus 1 to the 1. Our C2 was 2, so well, plus 2, x minus 1 squared, plus 4, x minus 1 cubed, and then plus 1, x minus 1 to the 4th. A little lengthy just because it's a degree 4, but kind of what WebAssign gave us. Any questions? So in general, we also want to at least want to mention the binomial theorem. Let's suppose we have a polynomial. One plus x to the n. And if we want a power series representation of this, again, it's polynomial. So the power series representation is just the polynomial. The problem is that it's not expanded. So this is going to be equal to some C0 plus C1x plus C2 x squared, and it's going to go all the way up to degree n. And we want to be able to find these constants. So I could literally multiply all this out. The problem is with just an arbitrary n, since we're coming up with a formula for this for an arbitrary n, we can't really expand it out. Right? At degree 4, we could expand out, come up with the explicit constants. At degree 5, we could expand out, come up with the explicit constants. But now that my power is a variable itself, it's going to be hard to come up with an explicit formula just by expanding it out. So we want to go through our techniques we were just using to go through that. And this is just going to be a Maclaurin series. So we're just going to be at x equals 0, centered at 0 there. So nothing fancy in terms of what we're plugging in. And hopefully that'll save some of our calculations. So let's try to go through it quickly here. So f of 0 is, of course, C0. F of f prime of x gives me, oh, sorry, I didn't even evaluate it. And actually, let's put them over here. So let's keep our table organized since we want to go through several of these, and we want to come up with a formula as well. Since we're not just doing explicit numbers, I want to organize it in such a way that we can organize or recognize a formula out of that. So our f of 0, when I plug in 0 here, it'll be 1 to the n. It'll be 1, and of course that will be our C0. F prime of x is going to give me n, 1 plus x to the n minus 1. F prime of 1, excuse me, f prime of 0 is just going to give me n. When I take two derivatives, we'll have n times n minus 1, 1 plus x to the n minus 2. And of course, when I evaluate it, we will get n times n minus 1, quantity n minus 1. So if that guy's our C1, this guy is not quite C2, right? Remember, this is 2 times C2. I would need to divide this guy by 2 factorial to get that. You can kind of see the pattern. What's going to happen when I take 3 derivatives? It's going to be n times n minus 1 times n minus 2, 1 plus x to the n minus 3. And every time I evaluate at 0, well, this term is always going to be 1, because it'll be 1 to some power. And all that's going to remain are these constants. N minus 2 times n minus 3, n minus 1 times n minus 2. And that's going to be our 3 times 2 times C3. And so what is our pattern if we kind of kept continuing with this? Well, my nth derivative, and actually let's use our kth derivative since n was the degree of the polynomial. So the kth derivative, what are we going to have? We're going to have n times n minus 1, n minus 2. And how far down are we going to go? Well, this is a degree 3, and we stop at 2. Second degree derivative, we stopped at n minus 1. So this will be n minus k minus 1. So if I'm taking 4 derivatives, that'll be n minus 3 is where we stop. And then, of course, we have our 1 plus x to the n minus 3. So sorry, my columns are going to overlap here a little bit. When we evaluate that, at 0, of course, this term is just going to be 1. So we will get those products. And it's almost looking like a factorial. Common notation, it is written in factorial, but if we want to use it for potentially fractional powers of n, not going to quite make sense. So we will have n times n minus 1 times n minus 2 times n minus, and we can simplify this. So that's n minus k plus 1 if we distribute that negative sign. And so remember, this guy, it's not equal to Cn, it is equal to, since I took k derivatives, it is equal to k factorial times my kth constant. In other words, my ck is going to be n minus 1, n minus 2. You're going to keep taking products, but you're going to stop at n minus 1 degree less than k, and then divide by k factorial. This notation, if you've had to take any sort of probability course or statistics course, if you have to, hopefully most of you guys will take a statistics course for your undergrad. I'm not sure what your majors are, but statistics is definitely a good thing to have, especially in today's world. I think it goes a little bit further than a lot of calculus, just in terms of interpreting and understanding data, how to work with data sets. You will see this notation a lot. This is called the binomial coefficients, and we often write it as a parentheses. There's no line here, so it's not dividing. This is just a notation, and we read it as n choose k. It comes up in probabilities. It's the way that if I have n total objects, how many different ways can I arrange them in k groups? So if I have 10 people and I want to choose 2 of them to form a committee or something like that, it's going to be 10 choose 2. And we can plug in the number of ways we can count how many different committees of 2 people we can form if we're pulling from 10. It naturally comes up in this polynomial expansion. So we write our series like this. So k is going to be our index. And it's just written like that, since this is kind of hard to write out. So we just shorthand, that's notation for this guy. Any questions so far? Let's go through one example of this, just because it is practicing using these formulas. We only got 5 minutes, so I don't want to start adding Taylor series together yet, since that might take a little longer to explain. We can start with that example tomorrow. One thing to note, since we're talking about simplifying factorials, is that when you see this, it's often written as n factorial over k factorial times n minus k factorial. This is how you most often see this. And so why does this work? Remember, when we have factorial, so something starting at n, this is n minus some number. So this one's going to be a little bit smaller. You could write out the numerator as n times n minus 1 times n minus 2. It's going to keep going. Eventually, I'm going to get to n minus k plus 1, n minus k, n minus k minus 1, and then it's going to keep going. So this is my numerator. I just wrote out the first couple terms of the factorial. It's going to keep going. I wrote out these terms in the middle for whatever k value is. So near k, right? Eventually it'll have n minus k, one more than that. And the one below that's going to be n minus k. The one below that's going to be n minus k minus 1. And if you notice that this n minus k factorial is just this part. So in the denominator, when I have this n minus k factorial, if I wrote this term out and expanded it, it would be n minus k minus 1. And so all of those divide with this guy. And we are left with the formula as we saw it, right? N times n minus 1 all the way down to k plus 1. And our denominator is k factorial. This doesn't quite help us because, so question. Doesn't hold for fractions. This is one of those weird things where if we wanted to find a power series for something like square root of 1 plus x, it turns out we can actually use the formula that we just derived, even though here we kind of assumed that n was an integer, but even if n wasn't an integer, if I went through this process, nothing would change, right? There's no chain rule because it's just a 1. I would still have whatever fraction that n was, and then reduce the power. And then I would do it again. And even though these n's and n minus 1s and n minus 2s would be fractions, we would still get the exact same formula. So it still holds. And if we want to come up with a power series for this guy, let's go through it real quick. So let's keep our formula kind of handy here. So our n is equal to 1/2. And then we can just find our constants. So our C0 is going to be essentially 1/2 divided by 0 factorial. So that's just going to be 1/2. Actually, hang on, that should just be 1. What do I choose? That's a technical point. I don't want to spend it since we're out of time. Our C1 should be our 1/2 over 1 factorial. And then we would go to 1 less, which is going to be, n minus 0, which would give us that. So our C1 should be 1/2. Our C2 is going to be 1/2 times negative 1/2 over 2 factorial. And we can keep going like this. So our C3 is going to be 1/2 times negative 1/2 times negative 3/2 over 3 factorial. And we can simplify all of these and then come up with a Taylor polynomial that will approximate our square root function. We can finish that one tomorrow if you guys want. Any questions?
Yes, I have one question, and it's about the what's on the calendar here. I'm going to pull that up.